All right, so let's get started. Today we want to start chapter 3, and chapter 3, the whole chapter is on potential, and basically here we want to learn a few tricks that we can calculate electric potential for various electrostatic problems. Okay, the tricks we're going to learn here, some of them are actually beautiful, some of them are based on physical intuition and concepts, and some of them are mathematical tricks. Some of them you might have been familiar from your other physics or mathematics courses, and I guess some of the methods you are familiar from your course on differential equations. Okay, so I'm going to first give you an overview of what whole chapter looks like. Okay. So what we're going to do at the beginning is that we want to look at how we can calculate electric field, and I'm going to point out that's not easy to do it directly from any charge distribution. Then we're going to look at the potential, and then we're going to look at the differential form of the Laplace's equation. Okay, so we had Poisson's equation, we had Laplace's equation. A lot of times we are interested in calculating electric potential in a volume or in a space that there is no electric charge distribution. That does not mean that there is no electric field. The point is that a lot of times we have electric charges distributed around a space or on the boundaries or somewhere, but then we are interested on how this electric field and electric potential are distributed in a space away from those electric charges, okay? So because of that, the focus becomes on Laplace's equation, which is a differential equation for electric potential away from any electric charges, okay? So that Laplace's equation is not necessarily a trivial, easy differential equation. It can be difficult, okay? It can be difficult because if you are in 3 dimensions, it's going to be a second order partial differential equation with 3 variables. Okay, there's no general solution for such equations. Okay, and then depending on the boundary condition, this can be difficult as well. Okay, there is something very specific about Laplace's equation and most differential equations of this type, and that is the solution of the equations are unique. Okay, so what does it mean, the solution of the equation is unique? The thing is that there's only one and only one solution for that equation given the boundary condition, okay? That means if you want to solve that equation, okay, if you cannot do it in a proper mathematically tractable path, but if you can have a shortcut and somehow come up with a solution that satisfies the equation, okay, so let's imagine somehow, okay, by a shortcut or by a guess or whatever, you come up with a solution that satisfies the Laplace's equation and also satisfies the boundary condition. As soon as you come up with such solution, you already know that this is the answer and this is the only answer, okay? So this is very specific about Laplace's equation, and that's very interesting. And what we're going to do in this chapter, we're going to use 2 different methods. One of them is the method of image charges. And that method is based on certain physical intuition, okay, that you construct the potential of the space you are trying to find based on some assumption of maybe the system is very similar to a different system. But then we will find that the electric potential for a hypothetical system satisfies Laplace's equation and satisfies the boundary conditions. And then as soon as you find that, that is the solution. Okay, so this is one of the methods we're going to discuss in this chapter. Probably not today, but next week, Thursday or next week, we're going to discuss the method of image charges. And the other method is very mathematical, and that's actually beautiful, is method of separation of variables. As I said, Laplace's equation, you solve that in 2 or 3 dimensions, okay? And you have potential, which is function of x, y, and z in space, okay? So method of separation of variables is a mathematical tool that you assume your potential is a multiplication of 2 or 3 different functions, each of them only a function of a single variable. Let's imagine v, x, y, z is a function of, is multiplication of function number 1, which is only function of x, times function number 2, which is only function of y, and function number 3, which is only function of z. Okay, so that's, with that construction, you can simplify the equations. Again, this doesn't work for any problem, but if it works at the end, if from that method you can find the potential that satisfies boundary condition, satisfies Laplace's equation, that's the solution you are looking for, okay? And for some of the problems, it works beautifully, and it's amazing how nicely it works out. Okay, so this is gonna be the whole chapter. We're gonna do a number of examples. I expect like we spend like 2 or 3 weeks on this section. Okay, so today I'm gonna go through the basic stuff. I'm gonna introduce Laplace's equation again. And the approach for discussion today is that we start from simple case, one-dimensional Laplace's equation, which is ordinary, second order, very basic and simple differential equation. Then we move on to second order, two-dimensional Laplace's equation, okay, which has a little more features and interesting stuff into it. And then I'm gonna introduce the three-dimension, and we're gonna have certain discussion on that and certain mathematical proofs on that as well. Okay, and then after that, I'm going to talk about the boundary conditions and uniqueness theorem. And uniqueness theorem is the same concept that I said, that if you find the solution of the Laplace's equation, that's one and only a solution for that. Okay, and if I have time, I'm going to start one basic example on the method of images. Okay. So, any questions so far? Looks good? Okay, so with this interview, I'm gonna...
Professor, we're still on chapter 2, right?
No, we are chapter 3.
Chapter 3, okay,
yes.
Sorry.
Yes. Okay, so again, to begin with a little step-by-step, electrostatics, okay, so one goal of the electrostatics is to calculate electric field created by a stationary charge distribution, okay? So you have certain charge distributions, let's say you have rho, maybe some surface charge density sigma, and maybe some linear charge density lambda. Imagine you have combination of these. At the end, we are trying to find electric field at any position, let's say R, as a function of this charge distribution. Okay, so one way is doing the integration over all these charges. Okay, so 1 over 4 pi epsilon 0 dq over r squared. The r in the denominator is a separation vector times r hat. Okay, so basically this integral gives you electric field as a function of your charge distribution dq. Okay. Now, is it an easy integral? Most of the time, no. Most of the time, it's just way too difficult. If you want to calculate it numerically, you can do so. Sometimes that's not easy either, but this is the whole basic idea of how to relate electric charge distribution to electric field. The problem with this integral is too difficult. Okay, so another way we define was we work with electric potential and relate electric field to electric potential. Okay, so electric field integral looks kind of similar, but the main difference is that electric potential is a scalar field and is a scalar, and it's much easier to conduct this integral. Okay, and from this to this point, if you calculate electric potential, you know that electric field is negative of the gradient of the electric potential. Okay, so if you find electric potential, you can calculate it. Okay, we did a couple of examples that we calculated electric potential based on this integral. Okay, and from that we could calculate electric field. Okay, this is one way. It makes things a bit easier. Okay, maybe a lot easier, but it's still, this is not an easy, trivial integral to carry out, except for the cases that we have a spatial symmetry, a spherical symmetry, and very special, simple type of geometries. Okay, so what we're going to do in this chapter, we're going to forget about these two, and we're going to focus on the differential form of the Poisson's equation and Laplace's equation. Okay, so differential form of this equation is basically the Laplacian of the electric potential, which is rho divided by epsilon 0. Okay, so this is the Poisson's equation. Okay, this is a Poisson's equation and relates the Laplacian of the electric field to the charge density. Okay, and as I said earlier, a lot of times we are interested in potential, but we are not exactly on the positions that we have charge distribution. We are away from charge distribution. So rho becomes 0. And then the equation that we need to solve, the differential equation, is Laplacian of the potential is 0, and this is the Laplace's equation. Okay. Equations of this type, Laplace's equations, are very common in physics. You will see the same sort of equations in thermodynamics, in heat transfer. You see the same sort of equation in diffusion equations. Okay, so this is very common, and one of the places that we work with this a lot is electrostatics. Okay, so now the equation is this, and this looks very simple, right? If I want to expand it, the whole thing that we're dealing with is basically this differential equation. Okay, so this is, I would say, basically the differential equation that we are dealing with for the whole chapter. The equation looks very simple in the sense that the second derivative is 0, but the thing is that this equation alone is not going to give you the potential. This equation and boundary conditions combined are going to give you the solution for the Laplace's equation, okay? And all the electrostatic properties and charge distributions and whatnot are in the boundary conditions, okay? So far, clear? Everybody? Okay, so I want you kind of forget about these things and just focus on this one and knowing that this is the equation that we need to solve to find electric potential. And the rest of the discussion, I'm going to look at this in 1, 2, and 3 dimension. Okay, and I'm going to discuss certain behavior of the solution of the Laplace's equation. All right? So let me clear up the board. Okay, so let's look at a one-dimensional case. Okay, one-dimensional case means the function v is only function of one variable, let's say x, and not function of the rest. Equation becomes simple, becomes second derivative of v with respect to x. And if it's only function of one variable, we don't need to use partial equations, so that becomes d is d2v over dx2 is 0, okay? And what is this equation? This is a second order differential equation. It's ordinary. I would say this is the most simple second order ordinary differential equation, okay? What is the general solution for this equation? V is m times x plus v, okay? So this is a general solution. We have two fitting variables, m and b, and these two variables will be calculated based on the boundary condition, okay? So now if you look at this, this is the equation of a line, okay? It's a simple line, and if I want to plot it, we can say, if this is v, I need two boundary conditions to find what should be m, what should be b. And that means if I'm looking between these 2 points, okay, between x1 and x2, and imagine just my boundary condition at these positions, I need one v variable here and another v variable here. And what this solution is just a straight line connecting the 2 boundaries. Okay, so we have 2 boundaries, and then the solution of Laplace equation just connects these 2 boundaries. The slope m is calculated based on these 2 boundary conditions, the same as b as well. Okay, so the constants here are calculated based on the boundary conditions. Any second order ordinary differential equation, at the end you need 2 variables, 2 fitting variables, okay? And those are determined based on the boundary condition, okay? So one-dimensional case is as simple as this one. Okay, so now in this solution, there are 2 things that I want to highlight. Okay, and those 2 things may be way too obvious here. It may even look silly that I'm highlighting them, but those are important because those are the 2 characteristics that the solution of the Laplace's equation retains if when we discuss 2-dimensional and 3-dimensional cases one. Okay, so I'm gonna make here a star. So I'm gonna put 2 stars here, okay? And these are the 2 characteristics that we're gonna come back for 2 and 3-dimensional cases as well. So one of the things is here, this is a straight line, right? This is a straight line with a certain slope. If you look at any point on this straight line, that point, let's say, I'm gonna say Vx, okay? This is the average of the 2 points at the same distance on the left and right side of the point, okay? And what I mean is this: if we move a distance, let's say a to the right, and if we move the same distance a to the left, Vx is the average of V at x plus a plus V at x minus a. Okay, meaning that at any position you are, you can look at your neighbors, the same distance at the left, the same distance at the right. Your value is the average of your neighbors. Okay, if you look at Vx, this is average of Vx plus a, the point here, and the average of Vx minus a, the point here. Okay, and this is, as I said, is very obvious when you have a line like this. Okay, and I'm gonna write that in this, that V is V at x is the average of neighbors at x plus a and x minus a. Okay, so this is one characteristic. At any point, the value is average of the neighboring points. Okay, and there's a second characteristic which is in fact the direct conclusion of this, that directly comes from this, is that the solution of the Laplace's equation, as you see in one dimension, it does not have any local minimum or local maximum. Okay, if you have this solution, the minimum is here and the maximum is here. And of course, it's a straight line, so the mean and max within this range are at the boundary condition. There's no peak in the center, there's no well in the center or anything like that. There is no local minimum or maximum, okay, and all the minimum and maximum occurs at the boundary. Okay, so I'm gonna put the second star here and say there is no local mean or max. All right, sounds good so far? Is this more or less clear for everyone? Yes, any question? No? All right, so what I want to do is that I want to clear this one and now move on to a case that we have two-dimensional Laplace's equation, okay? So if you are in two dimensions, let's say you have x and y, the equation becomes d2v over dx2 plus d2v over partial y square is 0, okay? So now we have two variables, x and y, and this equation is not an ordinary second order equation anymore. This has partial derivatives with respect to x and with respect to y, okay? So as soon as we have the partial derivatives and as soon as we get out of the boundary of ordinary differential equation, things get a little interesting in the sense that we do not have the general solution for this equation anymore, okay? So this equation does not have general solutions that you can use and then find the constants based on the boundary conditions. Okay, so solving this really depends on what kind of boundary conditions you have and how you want to fit that. Okay, so I'm going to discuss that, and what I want to do is that I'm going to give you a physical example where the solution of the Laplace's equation is kind of physically understandable for you guys, and then based on that, I want to discuss the properties. Okay, so one case that in physics that we see that really a function that is a solution of the Laplace's equation forms in a physical way is where you connect, let's say, a surface of the bubble or something like a sphere, or something like, let's say, a rubber sphere. You cut it and put it on a box. Okay, so what I mean is this. Imagine you take a cardboard box, okay, and you cut all the corners and all the sides in random shape that you wish. Okay, imagine you take this and you cut one side like this, cut the other side, and this, and this. Okay, so imagine you make such a cardboard box and cut it like this. And then if you put on top of this, cover it with a rubber surface, okay, and make it super, super tight, okay, you will have a surface that is maybe bumpy a little bit, okay, but connects all the boundary conditions very nicely together, okay. And in fact, that surface that you see is a solution of a Laplace's equation. Where is the boundary condition? The boundary condition is exactly these points that you cut. Okay, so these are the boundary conditions. And the rest of that, if we connect this, okay, it's going to be a relatively simple function that is connecting the boundaries together. Okay, so this is one example that you can physically observe how the solution of the Laplace's equation behaves. Okay, and that is interesting because, as you can imagine, such function is not a complicated function in the sense that this is the most simple function that connects the boundaries together. Okay, this is the most featureless function. I say featureless in the sense that you will not have any specific spike or bump or anything right in the middle. What dictates the shape of the solution is only the boundary condition, okay? And if you connect this to the surface, in a most simple way, and that is the solution of the Laplace's equation. Okay, so the sort of shapes that if you use foam and bubble and give a ring the way that forms, okay, that actually follows the Laplace's equation as well. Okay, so that's what you want to think of the solution of the Laplace's equation, the most simple featureless function that connects the boundaries. Okay, and if you follow this, again, you will have these two features. Okay, so at any point in the center, okay, not on the boundary, at any point if in the center, if you draw a circle, okay, let's say this is now x and the other one is the y coordinates, okay, if you look at any circle and if you project that on the surface of this, any point in the center, okay, is going to be the average of all these neighboring points on the circle, okay? And that's something you can mathematically show that as well.
Professor, is this still for 1D?
No, this is for two-dimensional. This is function of x and y.
That's right, sorry.
Okay, so I just wanted to give you a nice physical, hopefully, I could give you a physical intuition of how the solution of the Laplace's equation even looks like. Okay, so just imagine you have a rubber membrane, you put it on top of this, and you actually stretch it as tight as you can. Okay, that's what you see. I mean, surface of the drum is something like this, but that's too simple because the drum does not have ups and downs on the boundary. Okay, but if we had, that would have been the solution of a Laplace's equation. Okay, so any point, if you choose a circle, and the circle of the center of the circle is average of all these neighboring points. Okay, so the same concept holds for two-dimensional case as well. The only difference is that the average is based on two-dimensional case, and here we have, let's say, v of x and y, which is average of neighbors at neighbors on a circle around x and y. Okay, and again, because of exactly the same property, okay, that any point is average of the neighboring points, you cannot have any local minima or maxima, okay? Because no point can be larger than the neighboring points or smaller than the neighboring points, okay? So the second one is correct in the two-dimensional case as well. If you have any maximum or you have any minimum, that occurs exactly right at the boundaries, okay? Beyond the boundaries, everything is kind of getting averaged based on what the boundary was dictating. Sounds good? Any question? Is it clear more or less? Okay, so if it's something not clear, it's good to ask right now. These are very conceptual discussion, not much mathematical. Okay, so if you interrupt me, that's a good thing. Okay, so if there's no questions so far now, I'm going to move on to three-dimensional case. Okay, so I'm going to look at the three-dimensional case, and the first characteristic that we said any point is average of the neighboring points. I'm going to prove that mathematically, considering that we have electric potential created by a point charge, and that follows the Laplace's equation, and I'm going to mathematically show that the electric potential at the center should be equal to the average of the electric potential on a surface of a sphere that surrounds that point. Okay, so let's look into that. Okay. Okay, so this is kind of three-dimensional case. Okay, and the first property, let's say this is the solution V of x, y, and z is a solution to the Laplace's equation. Okay, so the first property, I would write it mathematically in terms of the integral of any point. Okay, so I would say V of x, y, and z is equal to the average of the values of V on a sphere that surrounds x, y, z. That means if we are at this point, which is x, y, and z, the value of the function at this point is the average of the function on such a sphere like this. Okay, this value here is, let's say this is V of x, y, z. The average on the sphere is 1 over 4 pi r squared. Okay, if this is r. This is the area, and then we're going to integrate over the surface v dot dA. Okay, so this is what I want to prove, that the solution of the Laplace's equation, electric field created by a point charge, has this property that the V at xyz is equal to the average of the value of the function on a sphere around that point. Okay, and mathematically I would just keep this as this. Okay, so let me get rid of this. Okay, so what I want to show more precisely is this. Imagine we have a point charge Q. Okay, this point charge creates a potential, okay, in the space. And I'm going to call that V, X, Y, Z. V is a potential, X, Y, Z is three-dimensional parameters in Cartesian coordinates. Okay, so what I want to show is this. If we are at this certain distance from the charge Q, right here, okay, the value of the electric potential at this point is equal to the value of the electric potential is equal to the average of the electric potential on a sphere around this point. Okay, so I want to say electric potential at this point is equal to the average of the electric potential on this sphere. Okay, and the case we have here is electric potential created by this point charge. So we know what potential we have. Okay, so to look into that, I'm going to choose my central coordinate system be right at the center of this point. So this is going to be my X, Y, and Z. Okay, actually the other way around. This should be X, this should be Y. Okay, so we know what kind of electric potential we have from this, and we can look at the value here, and also we can look at the value on the surface. Okay, let's imagine the electric charge is sitting at distance Z from the center. Okay, and now what I want to do is that I want to look at the integral something like this. Okay, and by the way, the radius here is R. And at the end, you will see the conclusion is independent of the value of R. Okay, that means no matter how big the sphere you are considering, still the value of the potential at the center of the sphere is equal to the average of the potential on the surface of the sphere. Okay, so is it clear what we are trying to look at, what we are trying to show?
Yep.
Yes? Okay, any questions so far? We had no single question today. I hope everyone is following. Okay. So this electric potential for a point charge, we can write it as 1 over 4 pi epsilon 0 q divided by r, where r is the separation vector from any point in space to the point charge. Okay, so in this case, because the point charge C is sitting at the position plus C, the r separation vector can be written in terms of r squared is z squared plus r squared minus 2zr cosine of theta. Okay, and we're going to use the r values that are on the surface of the sphere here. Okay, and we're going to look at that integral. Okay, so the v, the average value, I would say, is 1 over 4 pi r squared. Okay, this is 1 over the total area of the sphere times the integral of v dA. V is 1 over 4 pi epsilon 0 q over r. The q and 4 pi epsilon 0 are constants, so I take them out of the integral. Q over 4 pi epsilon 0. Integral of, we have 1 over r, which is z squared, r squared minus 2rz cos theta, all under square root. And we have dA, and dA runs on the surface of this sphere, and that's going to be r squared sine theta d theta d phi. Okay, the whole thing here is dA, infinitesimal area in a spherical coordinates, where you are integrating over the surface of the sphere. Okay, so this integral and this term as a whole is this one. Okay, 1 over 4 pi r squared is the first term, and the rest, these are the constants from the electric potential. The whole denominator here is 1 over r, and the numerator here is dA, which is here. Okay, sounds good? Okay, so this integral, phi runs from 0 to 2 pi, and there's no dependence on the phi in the integrand, so that only gives a factor of 2 pi. D theta sine theta, okay, so we can use sine theta, d theta as one variable, and here we have cosine theta. Okay, so integration is not that hard. The integral, okay, as a function of theta becomes, I'm going to write V average is 1 over 4 pi r squared q times 4 pi epsilon 0. Okay, so the integral of d phi gives me a 2 pi factor. I'm going to add that here, 2 pi. And the rest are integral on theta, which are one over rz, square root of z2 plus r2 minus 2r z cos theta, and theta runs from 0 to pi. Okay, so We can simplify things a little bit. So by the way, we get R in the numerator here, not in denominator. Okay, so then we average. If we simplify a little bit, it's going to be Q over 4 pi epsilon 0. Okay, so Q over 4 pi epsilon 0, 2 pi and 4 pi cancels out, R cancels out with R. It becomes 1 over 2RZ times, if we use value of theta at pi and 0, we get Z plus R, because we get Z squared R squared plus 2RZ, and then minus Z minus R here. Okay. And what we have here is Z plus R minus Z minus R, and Z cancels out. Okay, so we have 1Z here, and then we get 2R. The 2R cancels out with this. As a whole, we get 4 pi epsilon 0 times Q over Z. Okay, so what I did here, I look at the average of the electric potential on the surface of this sphere. Okay, so I wrote this integral. V average is this integral. This is an integral in spherical coordinates. dA over R remains inside integral. The rest were constant. This integrand, the integral becomes this. Okay, so we had a bunch of constants here outside. And if you look at this, it has very interesting form of Z squared plus R squared minus 2RZ. Okay, and value of cosine at pi and 0 are plus 1 and negative 1. If you look at them under the square root, one of them becomes Z plus R, the other one becomes Z minus R. Okay, and it has this interesting shape that with the Z values cancel out. You end up having 2R that cancels out with these 2R in the denominator. And at the end, from all these constants and everything, we get a factor of 1 over 4 pi epsilon 0 Q divided by Z. Okay, and what is this? 1 over 4 pi epsilon 0 Q divided by Z is exactly the potential created by Q at the center of the sphere. Okay, so if you see, we calculated the average on the surface of the sphere. Okay, average of that on the surface of the sphere. Pretty involved mathematics here and doing all this integral, and at the end we get 1 over 4 pi epsilon 0 Q by Z, which is exactly electric potential at the center. Okay, and this conclusion is actually independent of how big the R is. Okay, so R is not necessarily something very small, so close to the center of this. This is correct for any point in the space and for any sphere that you imagine around any single point. Okay, so always, if you have point charge, you create a potential where the average on any sphere is equal to the potential at the center of the sphere. And that is interesting in the sense that we considered only one single point charge, but any charge distribution you can imagine is combination of many, many different point charges. Okay, so we have superposition principle always valid for electric potential, meaning that if we have Q here, if you add 10 more, 20 more point charges in a space, this conclusion is valid because this conclusion is correct for any single of those point charges, for any potential created by any single of those point charges. Okay. And you can also imagine if you move from discrete charge distribution to a continuous charge distribution, again, the conclusion is going to be valid. Okay, so bottom line, if you have electric potential created by any distribution of charges, you can always imagine one point, okay, and then you can look at the neighboring points, okay? The value of the potential at your point should be equal to the average of the electric potential on the neighboring points, okay? And This thing is actually has application in when you do computational work calculating electrostatic energy. Okay, what does it mean is this. If you want to computationally solve Laplace equation, what you do is that you iteratively look at your space and look at the potential at each space. The way you set it up is that you set it equal to the average of electric potential of the all neighboring points, okay? So this is not something we're gonna look at in this course, but if you take computational physics course, Tyler Luchko used to teach that course. I don't know if he's still teaching or not, but one of the topics and one of the projects in that course is solving Laplace's equation. And what you do is that for Laplace's equation, you always start by random, you guess a solution for the Laplace equation in a space, which may be incorrect, but what you do is that you keep correcting that by scanning the space and changing potential at any point equal to the potential average of the potential of the neighboring points. And if you do that iteratively, back and forth for any single point in your space, after a large number of iterations, you will come up with electric potential, which actually you will see satisfies Laplace's equation and satisfies boundary conditions. Okay, so these comments may be beyond the topic of this course, but I'm just telling you a bit of insight that this idea of any point is equal to the average of neighboring points is very powerful idea, and computational physicists use that to solve Laplace's equation. Okay, any question? Guys, you are not asking question, and I keep talking to the point that my voice is almost gone.
Yeah, I have a question.
Please.
I want to make sure that I understood this. So the result of the average voltage is it's telling me that it's exactly the same. It's an exact solution.
This is so. At any point, the electric potential is equal to the average of neighboring points. Okay, and that's always correct in electrostatics. Here we showed for one single point charge, but if you have any geometrically complicated charge distribution, it's going to be valid, because you can imagine those are made of combination of point charges. Okay, so if I have electric charges around in my office, and if I look at this point in the space, okay, if I want to calculate electric potential, one way is looking at all the neighboring points, measuring electric potential and looking at the average. This point is going to be exactly the same as average around this.
Ooh, okay.
Okay, and by the way, yes, this is exact, and that works for any charge distributions.
And also, it also follows the superposition principle, right?
Because electric potential follows superposition principle, we can expand our conclusion to any possible charge distribution.
Mm-hmm. Nice.
Nice, very nice. And it's actually something very powerful. As I said, computational physicists rely on this to solve the Laplace's equation.
Thank you.
Cool.
And this one also never has local min or max?
The same idea, yes. It does not have, because imagine if any point is average of neighboring points, that point cannot be a maximum, that point cannot be a minimum.
Oh, I see. Makes sense.
Right, it cannot be a minimum. So both of these conclusions, average and no local min or max, are true in three-dimensional case as well.
Gotcha. Thank you.
Cool. Okay, so if there's no question on this, I'm going to move on to boundary condition and uniqueness theorem. Okay, so we cover the basic stuff, and then we go to next step. So let me get rid of this. All right, so I mentioned a few times about the uniqueness of the solution of the Laplace's equation. Okay, so what I want to do now is that I want to prove, that there's only one solution to the Laplace's equation. Okay, and the way I want to prove that is this. I'm gonna first suppose there are two solutions. Okay, I want to suppose there are two solutions, let's say V1 and V2. And I'm gonna look at these two, and I'm gonna look at the difference between these two solutions, okay? And then I want to conclude that if there are two solutions, the difference between the two solutions must be zero at any point, meaning that the two solutions are in fact one solution, okay? So let's look into that. We're gonna check two cases, one of them where we have insulators, and in another case where we have also conductors in the space. Okay, so first, the more straightforward case, imagine we have this space and we are interested in solution of the Laplace's equation. Inside this space, there is no electric charge distribution, so the Laplacian of electric potential should be zero. And let's imagine on the surface we have electric potential V is specified on the boundary. Okay, so on the boundary, V is specified. Inside this space, we are trying to find electric potential following the Laplace's equation. Okay, so now let's imagine V1 is a solution that satisfies Laplace's equation and satisfies the boundary condition. Okay, so V1 satisfies and okay, so for any solution, we want both of these. We want a solution that satisfies boundary condition and satisfies Laplace's equation as well. Okay, Laplace's equation alone is not going to give you the solution. You need the boundary condition as well. Okay, so now imagine V1 having that feature, and now suppose there's another one. Okay, another solution V2 satisfies both of these as well. Okay, so imagine we have two solutions, V1 and V2. Okay, and now if we have two solutions, I'm going to look at V3, which is the difference between V1 and V2. Okay, so I'm going to say V3 is V2 minus V1. Okay, and that means V1 and V2 satisfy the same boundary conditions. V3 is a difference between the two. Okay, so from this one, I can directly say that on the boundary, V3 must be zero. Okay, because V1 and V2 are satisfying the same boundary condition. Okay, and if V3 is the difference between them, V3 must be zero at the boundary. Okay, make sense? Okay, so now V3 is zero at the boundary. The question is, does V3 satisfy the Laplace's equation? Let's look at the Laplacian of V. Okay, so Laplacian of V3 should be equal to the Laplacian of V2 minus Laplacian of V1. Okay, so V1 and V2 both satisfy Laplace's equation. Okay, so that means this is zero, this is zero as well. That means the V3 which is a difference between V1 and V2, satisfies Laplace's equation as well. Okay, so V3 is a function that satisfies Laplace's equation and is zero on the boundary as well. Okay, do you remember the example I had? I said for two-dimensional case, the solution of the Laplace's equation is, in fact, if you have a rubber membrane stretching it on a boundary. Okay, and I said the Laplace's equation is the most simple featureless function that connects the boundary. Okay, now imagine, think of V3. V3 is zero on the boundary. Okay, it has no maximum or minimum on the boundary, is flat zero. Okay, and V3 follows Laplace's equation as well, so it should satisfy Laplace's equation. What is the most simple case? What is the most simple case function that connects all the zero on the boundary together? It's a flat function being just zero, right? So V3, as a matter of fact, is just zero everywhere, okay? And if our conclusion is that V3 is zero, that means V1 and V2 should be exactly the same function, similar to each other, okay? Make sense? So here, idea is this: we want to prove the uniqueness. We want to prove that there is only one solution for the Laplace's equation, okay? And the approach was this: let's suppose there are two solutions, okay? Let's suppose there is V2 and there's V1, and then we looked at the difference between these two, and we figured out the difference of V2 and V1 must be zero, meaning that there is always one and only one solution to the Laplace's equation. So this is a case that we don't have any conductor. We only have one space that we are trying to find the Laplace's equation, and the boundary condition V is specified under boundary condition. Okay, this case is very, very general. The only limiting assumption for this case is that we do not have any conductor in a space, because conductors can change situation a little bit. The next part is going to be looking at the uniqueness theorem where we have conductors. Okay, sounds good? Clear? More or less? Any question? No? Okay.
I think I have a question.
Of course.
Regarding the definition of the Laplacian. So since the Laplacian is defined as zero, it implies that it's looking for the most simple solution to figure out what V is.
Yeah. So for the V3 is very special in the sense that it needs to be zero on the boundaries, because V1 and V2 are satisfying the same boundary condition. So if you look at the difference between them, V3 must be zero all the way on the boundary and on any single point on the boundary. Okay, so that's what we have about V3 on the boundary. And V3 is also satisfying the Laplace's equation, means Laplacian of V should be zero. Okay, so if we have zero on the boundaries, okay, and Laplacian is zero as well, this is the trivial solution for such equation. V3 just be zero. Sounds good?
Yeah, thank you.
Okay. So another case that I'm going to look at is the case that we are in a space with some conductors, okay, that they can possibly carry certain electric charges as well. They can be neutral as well, but let's assume that they have certain electric charges on them, okay? And then I'm going to show that the electric field that is created by these point charges is unique in this space, and that means electric potential will be unique as well. Okay, so let's first draw, and I'm going to explain what kind of geometry we have, and then we're going to look at more detail.
Professor, what you just erased, was for boundary conditions, right?
Yes, that was a space and the boundary condition.
Okay.
Okay, so what I'm drawing now is a figure 3.6 from your textbook. Okay, so I'm gonna look at the space that we have, let's say, number of pieces of conductors, okay, and they can have a specific charge distribution on them. Let's say QA, QB, QC. And let's imagine these are the total charges on the conductors. You can have as many as you can, okay? And then the whole thing is inside the huge boundary that is conductor as well. This huge boundary can be as big as going all the way to infinity, okay? So we are in a space that we have certain conductors with certain total charges on them. We don't care what is the specific distribution of charges on this conductor. So what we care about right now is that how much is the total charge on the conductors, okay? And inside the space, we can have certain charge distribution as well, okay? So we can have certain volume charge density. Rho can be zero, can be non-zero as well, okay? So what we are trying to find is that we are trying to prove that the electric field inside this space is unique, okay? And I'm gonna do very similar approach. I want to say, okay, what if it's not unique? If it's not unique, that means at least we have two solutions for the electric field inside the volume, okay, this volume. And then let's look at those two and let's look at the difference between them. Okay, so the idea is that let's suppose we have E1 and E2 that both satisfy the boundary conditions and Laplace's and Poisson's equation. Okay, here because we are assuming some non-zero volume charge density, the equation for the Gauss law is divergence of E1 and divergence of E2 should be equal to rho in a space. Okay, so these E1 and E2 are actually the electric field in the space that where we have charge density. Inside this conductor, there's no electric field, okay? Outside this boundary, we don't even care. Okay, so the space we have is just this. Rho, as well as some conductors, those conductors can carry a specific charge. QA, QB, and QC are the total charges on the conductor. They can be zero as well, if you wish, okay? But they can be non-zero as well. Okay, so if there are two solutions here, meaning that means divergence of E1 should be rho over epsilon zero. Rho is the volume charge density. Divergence of E2 should be rho over epsilon as well. Epsilon zero as well. So these two electric fields have the same divergence. Okay, that doesn't mean they are necessarily the same, but the divergence must be the same because that's what physical charge distribution we have. Okay, and if we integrate electric field around each conductor, okay, E1 times dA should be 1 over epsilon 0 Qi, and this is the total charge on each conductor, okay? And these integrals that I'm showing here, like E1, these are integrals on a surface that is super, super close to each of the conductors, okay? Something like this. So this integral is on such surface, okay? And this must be correct for E2 as well. Sounds good? And so if there are two solutions, both of them should satisfy both sets of equations, and now I'm going to again look at the difference between the two. I'm going to look at E3, which is E2 minus E1. Okay, so because the divergence of E1 and divergence of E2 are the same, satisfying the same charge distribution, the divergence of E3 must be 0 because this is simply the subtraction between the two. So divergence of E3 is 0. Okay, so I'm now focused on the difference between E1 and E2. Okay, so that the divergence is 0, and for any of the conductors, okay, if we subtract E1 and E2 and integrate, because this integral are exactly the same as the total charge on each conductor, I will say the integral of E3 dA around each conductor has to be 0 as well. Okay, so now from E3, we have these two pieces of information. Okay, so far we cannot show that E3 is necessarily 0 to conclude that E1 and E2 are the same, but we have these two pieces of information that divergence of E3 is 0, okay, and the integral of E3 around any area of the conductor is 0 as well. Okay, so if the divergence of E3 is 0 everywhere, if we run the integral over all the boundaries, okay, if we run an integral over all the boundaries that cover conductors, let's say this one as well, and this one as well, and also the exterior boundary, okay. If we calculate integral of E3 dot all this area, that must be 0 as well. Because the divergence is 0, that means integral of E3 times dA must be 0 over all boundaries combined. Okay, so we have these pieces of information as well. This one is for each boundary. Sounds good? Okay. So I'm going to erase this part, and we need one more set of information. And with that, combined with these, we're going to conclude that eventually E3 has no choice than being 0 everywhere. Okay. And that's going to help us conclude that E1 and E2 must be the same. Okay. And the next piece of information is coming from looking at something specific but very helpful in this case. Okay, let me get rid of this. Okay, I'm going to look at this combination, divergence of V3, okay. V3 is the electric potential that is calculated based on E3. Okay, so if E3 is an electric field, V3 can be electric potential based on E3 in a way that the gradient of V3, negative of the gradient of V3 is equal to E3. Okay, so I'm going to look at the divergence of this specific thing, divergence of V3 times E3. Okay, and you will see why we are looking at this, because mathematically that becomes useful. Okay, divergence of this is equal to V3. If we expand it using the multiplication rules, this is equal to V3 times the divergence of E3 plus E3 dot gradient of V3. Okay. So now, if we look at this, the divergence of E3, we already concluded that needs to be 0. Okay, so the first term disappears. The second term, we have gradient of V3, and that is equal to the negative of E3. Okay, so the divergence of V3 times E3 is in fact equal to negative E3 squared. Okay. And this is magnitude of E3 to the power of 2, and the negative sign comes from the fact that gradient of V3 is equal to negative of E3. All right? Okay. So this divergence is equal to negative of E3 squared. Okay. And now, if we integrate this divergence over the whole space, okay, that we have inside, except inside the conductors, over this V, divergence of V3, E3 d tau, okay, this should be, following the divergence rule, it should be equal to the integral over all surfaces, all boundaries, of V3 times E3 dot dA. Okay, so this integrand is exactly what we had on the top. Okay, divergence of V3 times E3. From the first integral to the second integral, I am just using the divergence rule. It's completely mathematical step. Okay, we have divergence of this function. We're integrating over the whole volume. Okay, and that should be equal to the function itself integrated over all the boundaries. Okay, second one is a surface integral. The first one is a volume integral. Okay, so from this step to this step is only the divergence rule. Okay, but we also know that this function, this divergence is equal to negative of E3 to the power of 2. Okay, so that should be equal to, let me get rid of this one now, integral of negative E3 to the power of 2 times d tau. Okay. So now, if we look at this, this is V3 is a scalar, E3 is a vector function, and we are calculating this integral over all the boundary conditions. So what are the boundary conditions? These boundaries are around each of the conductors we have here, A, B, C, okay, and also on the outer boundaries, okay. So one point is that all these A, B, C pieces are conductors, okay. So if you look at electric potential on each of the boundaries, electric potential is a constant, okay? So what I want to do is that I want to write this integral, okay? I want to write this integral. Let me separate this in green, okay? I can write it in terms of separate integrals. And instead of saying all boundaries, I want to say boundaries on A, boundaries on B, boundaries on C, and then outer boundary. Okay, so that is like V3 times E3 times dA integral over, let's say, I'm going to say surface A, and then plus V3 E3 times dA on surface B, and so on. So surface A is surface of this conductor, surface B is surface of this conductor. We can have as many as conductors we have, and we have also exterior boundary as well, okay? So this green integral can be written in terms of many of these integrals, okay? And now look at this, V3 on each of these surfaces is constant, okay? So this V3 can be moved outside of the integral. I'm gonna say V3 on the boundary A. The same goes with this one, okay? Either this is a closed surface. V3 is a constant on the surface of B. So I can write this in terms of V3 on the surface B. The V3 is a constant, so we could take it out of integral. So we have, this integral is technically equal to one constant times the integral of E3 dot dA on one of these surfaces plus another constant times E3 dot dA on another surface, and it goes on, depending on how many conductors we have here, okay? But we had one conclusion from the first part, that is E3 times dA on each boundary needs to be 0, okay? That means each of these integrals here, this thing is 0. And also this thing here is 0. So for each surface around the conductor, this part becomes just 0 plus 0 plus 0, okay? So as a whole, this integral in this green box is many, many integrals on the surface of these conductors, but each integral is 0, okay? So at the end, this as a whole must be 0 as well, okay? So if you integrate E3 to the power of 2 over the whole space, over the whole volume, that must be 0, okay? And if you look at this integrand, this is to the power of 2. This is magnitude to the power of 2. And think about this. This integrand can be either 0 or positive at any point in space, okay? It can never be non-zero anywhere, okay? Sorry. It can never be negative or positive, okay? So it has to be either 0 or positive here, okay? If the integral over the whole space is 0, that means that at any point in space, it needs to be 0. That means E3 at any points in this space that we have must be 0. And that means the difference between E1 and E2 must be 0. That means E1 and E2 are exactly the same fields, okay? I'm way over time, okay? So what I want to do is that I'm gonna stop here. I'm gonna recap these uniqueness theorems on Thursday morning as well, and then we will have quiz at 10:15, okay? Any question?
No.
Okay, so because we are over time, well, of course you can ask question if you want, but if you want, you can also look at this, read a little bit, ask question on Thursday morning as well.
I was just going to ask, the quiz is chapter 3. I mean, chapter
Chapter 2, yes.
Right. Okay. Sorry. Thank you.
Yeah, that was important question. Sounds good? All right, so you guys enjoy the rest of your day, focus on assignments, and then you will be fine on the quiz.
Thank you, Professor.
Thank you, Professor.
See you later. Bye.